Okay, imagine we take two identical pendulums and we take the two bobs, we displace each bob some amount to the right, and then we release the two bobs from that same displacement at the same time. So at every subsequent moment in time, they will each have the exact same displacement. Right? The bobs and the pendulums are identical, they have the same length, they have been taken from the 0 point at the same displacement. So everything is the same. Gravity acts the same. The tension is the same, everything. We say that their oscillations, the oscillations of these two systems, are in phase. Right? But what if we did something different and instead we pulled one of the bobs to the left and then we pulled the other bob to the right and let go? Well, the oscillations would be out of phase. Graphically, there's a difference between these two, in phase and out of phase. These things look different. So open your books to page 83, right? And you see, kind of in the middle of the page there, we have three different objects, object A, B, and C. And the displacement time graph is shown for each object. Object A and B, graphically, their displacement time graphs are identical, right? So that means they are in phase. And that's what it looks like. That's what the position time graphs look like for two objects that are in phase. The curve is exactly the same. Object C, on the other hand, is a mirror image of object A and B. Its graph is a mirror image of the graph of A and a mirror image of the graph of B. So object C is out of phase with A and B. Right? Now I want you to draw these into your notes, these three graphs, and state that A and B are in phase and C is out of phase with the two. Right. Okay, so we're moving on with phase. You could say we're moving on to the next phase of phase, but doing so would be a terrible joke. Okay, let's say we have these three different graphs, and just by looking at these, we see there's two different curves, and each of these is a displacement time graph. So add in to your notes displacement on the y and time on the x. Right? So this is x, t, x, t, x, t. And you look at these and you notice there's two different curves in each graph. So there must be two different objects which are oscillating, right? So instead of showing those different curves in separate graphs, now we're putting them together in a single graph. If you see something like this, the green object and the red object are mirror images, right? That means that they are completely out of phase because they make a mirror image. But there's a different shift, you might say, between the two curves. And here there's an even different shift from the other two between the two curves. Right? So in each example, the waves are off by different amounts. And in each example, we can describe how much of a cycle the two waves are off by. And that's what we're going to learn how to do. Okay? We use this thing called phase difference, which is the amount of radians or degrees, where one cycle equals 2 pi radians or 360 degrees. So it's the amount of radians or degrees by which two waves are off. Right? So phase difference is measured in degrees or radians, but in IB physics we're going to use only radians to measure phase difference. Here's the equation for phase difference. Phase difference equals the time difference, I'll explain that, times this conversion factor, 2 pi radians per time period, t, big T. So here's what time difference is. It's the amount of a period separating the first crest on the first wave from the first crest on the second wave. Right? And I'll show you what this is with an example. Time difference. It doesn't actually have to be measured from crest to crest. Instead, it can be measured as the amount of time separating, the first trough on the first wave from the first trough on the second wave, Or it could be the amount of time separating the first 0 point or node on the first wave from the first node on the second wave. So I want you to pause the video and work out the 3 examples. Show your work on the side to the right. And what I want you to do in each example is find the phase difference. Right? So to do that, you're going to have to find the amount of time, right? How much of a period is separating the first crest on the first wave from the first crest on the second wave. So how much time is separating that? And then you plug in that portion, that fraction of t. You plug that fraction of t in right here. So is it t over 4? Is it t over 2? Is it 2/3 t? What's the time difference? What's the amount of time separating the first crest on the first wave from the first crest on the second wave? And I want you to give this a shot and pause the video, but now I'm going to move on and do the answers. So I'm going to show you the answers. Here's how you do it. This is one period, right? From the first crest on green to the second crest on green is one period. That means half that distance, which is from the first crest on green to the first trough on green, this is t over 2. This is half of t. But this is also the time difference between green and red. Right? Because t over 2 is how far it takes along the x-axis to get from the first crest of green to the first crest of red. And that's what we define time difference as. So I plug in t over 2 into my equation for phase difference, and I multiply t over 2 times 2 pi radians per big T, and you find your answer. Here's the next example. I start with the same thing, right? Say, okay, it's hard to see what this time difference is, how much of t, how much of a period is separating these two things. So I'm going to start out by just drawing from one crest of green to the second crest of green. And I know this is one full period. And now I'm going to cut it in half, right? Which means I'm coming down, instead of going from here all the way to the second crest, I'm going to go only to the first trough. Or the next trough, I should say. So if this is t, then this is t over 2, right? Now I'm going to cut it in half again, which takes me from here. Well, now instead of going from here to here, I'm going to go from the first crest to the next equilibrium. And this is t over 4, right? This is t. Here's t over 2. Here's t over 4. And I see that t over 4 is the time difference. That's how much of a period. So that's how much of a period separates first crest of green from the first crest of R, t over 4. So I plug in that time difference, t over 4, into the equation for phase difference, and that t over 4 gets multiplied by 2 pi radians over big T, and you find your answer. Here's the last example. Right? Do the same thing. Here's a full period. It's from the first crest of green to the second crest of green. Right? So now let's look at what half of a period is. It's this. And here's a quarter of a period. Uh-oh, I overshot the time difference. Right? So the time difference, it's exactly between 1/2 t and 1/4 t. Right? Which means it's got to be what? What's exactly between 1/2 and 1/4? Right? That's for you to find out. So you plug that value, that much t, whatever fraction of t it is, and I want you to figure it out. We'll look at it in class. You plug that in for the time difference. You multiply it by 2 pi radians over t, and you find the answer for phase difference. We're going to skip this example problem, but we'll look at it in class. This will be how we begin next class. So turn to page 84 of your physics book, and I want you to take a look at the, we're going to look at these 3 examples that are shown. Right? We have headers that say photo gate, force sensor, position sensor. We can use a photo gate to measure the period of oscillation for a pendulum. the way you set it up is so that it's shaped like a U, right? And it's so the bridge of the photo gate is sitting on the ground like you see in your book, and you hang a pendulum down and you pull it away, but you arrange the pendulum so that the 0 point, right, the 0 position, causes the bob of the pendulum to be breaking the beam, the laser beam, of the photo gate. So what you do then is once you have that 0 position aligned right inside of the beam of the photo gate, you pull the photo gate over to the side, you let go, and every time it passes, every time you pull the pendulum to the side, the bob, and you let go, and then every time the bob passes through the 0 position, the photo gate's beam gets blocked. And whenever that photo gate's laser beam gets blocked, it sends a signal to the computer, and the computer logs the time when the signal was received. So we can use this to measure how much time passes between successive blockings of the photo gate, and really that's telling us how much time passes between successive 0 points. We can also use a force sensor, right? So the Y component, clearly, the Y component of tension changes over time as the angle changes, right? In other words, as the pendulum swings back and forth. So when the pendulum is all the way over to the side, right, the Y component of tension is going to be kind of small because of that big angle. But when the pendulum is straight up and down in the 0 position, the Y component of tension is simply the same as the total tension in the string. But as the angle gets bigger, as it moves farther away from vertical position, the Y component decreases. So it changes over time. If we connect a force sensor to the top of the string, right, as you see in your picture, so that the top of the string is connected to the force sensor, the bottom of the string is connected to the pendulum bob, then what we do is we can use that force sensor to effectively measure the Y component of tension. And readings are collected by the force sensor over time, right? It logs values of force measured by the sensor as time progresses, and it creates a graph. So the resulting force versus time graph would show us the period, because we could identify when the tension is biggest, right? When the Y component of tension is biggest, and that's going to occur, Y component of tension will be biggest when we pass through the 0 position, because that's when all of the tension is in the Y component. And we can use successive force maximums, right? Successive peaks or crests of the force time graph to identify how much time is passing between 0 positions. And that can allow us to calculate tension. The time period, the period t. So we're going to do this experiment. We're going to actually do this in class. And the other cool thing is that damping is evident on the force time graph that you see on page 84. Damping causes the object to slow down, but velocity is related to the centripetal acceleration, and thus it's related to the centripetal force. Right? So because it's related to centripetal force, the velocity affects the tension, because tension is what provides the upward force, making this bob move in circular motion. So as the velocity decreases, the tension also decreases. Okay? Therefore, its Y component decreases, and this means that the biggest the tension ever gets, right, the maximum Y component of tension gets smaller and smaller, which is why those crests in the graph are getting less and less high. So we're going to do a little on wave characteristics. A mechanical wave is the propagation or the passing along of a disturbance through a physical medium. Right? It's when we pass a physical disturbance through a physical medium. What does it mean for a disturbance to be propagated? Well, a physical medium, and looking at what this means will help us understand. It's like a web of interlocked but movable particles. Right? So if you push one particle out of the way, if you displace it upward, for example, the adjoined particles, which are connected to it, will get pulled up along with it. right?